Before we really dive into the details of things like speaker design, it's really important to understand a little bit more about wave propagation in particular. And so I've got a diagram here, I guess, that shows it turns out this is a pin boundary beam that I had from another problem I worked some time ago, but it could just as easily be a string fixed and attached at both ends. And what we want to do is look at the response of this string if it's plucked. And so what you see here, so here's the boundaries. Here's the boundaries right here of the string. And if we were to grab hold of the string and pluck it, particularly if we did so at the center, you can see this oscillatory behavior here, where the string is vibrating up and down basically. And so you get a picture that there's a wave propagation in space between the boundaries of the fixed points of the string. And that's typically what's called a mode of the string, or sometimes the standing wave on the string. The other thing that's important to think about is the time domain response, because if you pluck the string, at some point the oscillations will subside. And if we were to look at what I've labeled the temporal picture here, you can see the time domain response of the string. And it starts out with a high amplitude as you displace it, of course, and then basically oscillates until it damps out, or the vibration of the string ceases. So the sensor that we place on the string, again right here, gives us a picture of what happens with the string at that particular point in space. And we could move that sensor to any other point on the structure, and the amplitude of the response, the peak that you see here, would reflect the peak response that you see on the wave. And so for this sensor, it corresponds to the response of the string through this slice of space, if you will. If we had put the sensor here, you would see a corresponding response that looked very similar, but with reduced amplitude, because the strings doesn't reach as large a vibration displacement. So anyway, just trying to tie together the fact that there is a spatial response to wave propagation in air or on a structure or string, and then there is the temporal response that we can measure at any point in time. And we're going to talk about how those two things relate to one another. So, for the spatial picture, we tend to talk about wavelength. Wavelength and spatial frequency. Wavelength's represented by lambda here, spatial frequency by nu, and a wave number k. Okay, and so the spatial frequency is related to the wavelength as such, and shown here. And of course, the wave number itself is simply 2 pi times 1 over the wavelength, or it could be represented as 2 pi times our spatial frequency. All right, and so it really describes the wave number describes the number of wavelengths that occur in 2 pi units. And so what I've done here is plotted out a sine wave, and of course this is 2 pi, and so it turns out that what I've shown here is one single wavelength over the domain of 2 pi. Now, for the temporal picture, so let's talk about the time domain. Remember, we talked about the spatial response that we see of the wave propagation in space, like the plucked string. Now we can talk about the temporal response. And the temporal response has a period of oscillation t, all right? And t is related to, so t is our period of oscillation, f is our frequency of oscillation, and we have a circular frequency. And the frequency of oscillation is related to the period 1 on t. So this is the time required for the one complete period of the cycle. And then, of course, omega is what's called the circular frequency, and that's equal to 2 pi times 1 on t, which also omega equals 2 pi times f. And what I'd like you to recognize is the analogy between the temporal picture and the spatial picture. If you remember in the spatial picture, and let me just slide back up to the top of the slide here, we see that k is related to 2 pi on lambda, which equals 2 pi times nu. And if we go down to the bottom here, we see omega equals 2 pi on t, and it also equals 2 pi f. So the point is that omega is analogous to k, our wave number, and lambda in the spatial domain is analogous to t, the period in the time domain. And then, of course, f, our frequency in the time domain, is analogous to nu here, right, in the spatial domain. So we're describing a wave basically either in space or time. And we have different symbols to represent the two, but they're analogous to each other. Okay? And so I can do the same thing with in the time domain. I can represent the same sinusoidal response characteristic, and this just happens to be one period of oscillation. So the amount of time it takes here is one period of oscillation for this particular wave, all right, to propagate. Now, when we move to sound wave propagation in air, we can easily relate the wavelength to the frequency, and that's done through the speed of sound, and so in air in particular. And so before we get into those details, we need to define a few basics. So we need to define our, we'll do it at room temperature. That's what we're going to be working at, especially around the concept of speaker design and typical acoustics in the musical range. But speed of sound in air is roughly 340 meters per second, 343 at 20 degrees C. And then the density of air, which is important as well for some of the calculations we make, is 1.21 kilograms per meter cube. And you notice that I'm working in the metric units here. All right. So the relationship between wavelength and frequency of sound in air is fairly simple. And it's expressed here. Lambda, the wavelength of the frequency, the wavelength, spatial wavelength, is related to the speed of sound in air. Remember, that's in meters per second, and frequency is in 1/seconds. So, if you look at the units on this, you have meters per second divided by 1/second, which gives you units of meters. All right, and that makes sense because the wavelength is going to be represented in a measure of meters. So let's talk a little bit about the relationship between our audible range and then, of course, the wavelength of sound in the audible range. So humans actually hear sound in wavelengths that range from about 20 hertz at the low frequency to 20 kilohertz at high frequency. And the older you get, actually, your response at higher frequency decreases. We know that, but at birth, basically, you have a range of 20 hertz to about 20 kilohertz, and it varies from person to person depending upon auditory capabilities. So, you've just computed the wavelength of sound at 20 hertz. What is the wavelength of sound at 20 kilohertz? Well, it's pretty simple. All you have to do is divide that by 1,000. And if you do that, you get a wavelength of 1.7 centimeters. So if our audible range is from 20 hertz to 20 kilohertz, that's the frequency range over which we hear, it corresponds to wavelengths that range from 17 meters to 1.7 centimeters. So the wavelength of sound at 20 hertz is 17 meters long. Now that's a large wavelength. If you think about look around your surroundings at your room, most of you probably aren't in a room at this point in time that has a dimension of 17 meters in any given dimension. So this is a really long wavelength, particularly compared to the size of your head and the distance between your ears. At high frequency, though, at 20 kilohertz, for example, wavelength's only 1.7 centimeters long, so it's very short. So this is important because it's important in particular in relation to how we actually localize sound.